Good afternoon. On behalf of Zestron, I'd like to welcome you to this session of our cleaning webinar series. I'm Marty Drechsel, the Technical Marketing Manager for Zestron, and kind of your guide for today's webinar. Today's presentation is on why SIR is the cornerstone of characterizing electronic materials. Just a few practicalities for our session today. All participants will be in listen-only mode. If you have questions during the webinar, and we certainly encourage you to ask any questions, please use the question panel in GoToWebinar. It's probably on the top right of your screen, a little chat bubble with a question mark in it. You can type your questions in there, and our presenters will address questions at the end of the presentation. If you have any trouble hearing our presenter or other technical difficulties, please use the raise hand button on the React panel on the lower left of your screen, and I'll send you a chat and we'll figure out anything that we can do to help you. This webinar is recorded and will be made available to all the participants. However, please remember that the content is copyright of Zestron and Gen3 systems. Please contact us if you'd like permission for reuse of content or images. Zestron is happy to have guest speakers today as part of our Academy series. Gen3 Systems is a leader in the SIR and electronics industry, so we're quite happy to have them as our subject matter experts. Today's speakers are Andy Naisbitt, the CEO of Gen3 Systems, and Dr. Chris Hunt, their CTO. Andy's led Gen3 since 2020. Driving innovation at a company with a 40-year heritage in designing, engineering, manufacturing, and supplying test measurement and production equipment to the electronics industry. Under his leadership, Gen3 has broadened its product range, streamlined production, and advanced innovation. Andy has also overseen a strategic expansion of the brand, positioning Gen3 as a leader in education and objective evidence for electronics reliability. Committed to continuous improvement, he ensures the company remains at the technological forefront while safeguarding customer confidence and long-term reliability in electronic systems worldwide. Dr. Hunt is leading all the technical development across the Gen3 company's product portfolio. From 1995 to 2016, he built and led the electronics interconnection team at the UK's National Physics Laboratory. He later led a spin-out to commercialize a patented conductive textile technology he invented at the NPL. Active in standards since 1995, he's chaired several standards and contributed extensively to the IPC standards. So we welcome our guest speakers. And at this time, I will turn it over to Andy and Chris.
Okay, well, thank you very much, Marty, for that introduction. Just going to get the presentation all set up. So yeah, thank you very much to Zestron for hosting us today. As you said, my name is Andy Naisbitt, the CEO at Gen3. And alongside me, Dr. Chris Hunt, our CTO. And we're going to talk through SIR and the cornerstone of characterizing it for electronic materials. So to get started, what reliability are we concerned about? Circuit assemblies can fail due to a number of issues, whether it's wear out or maybe an integrity failure. This isn't necessarily a design issue. The circuit hasn't suddenly changed. It can be a materials problem. And this can be expensive. So potential failure causes, this can be a device failure, it could be mechanical or flexing, it could be corrosion, it could be in the component, damage to the silicon, the dielectric, the packaging, or even the PCB assembly. So maybe solder connections of components, or generation of short by corrosion, or even inside the PCB where corrosion could occur along glass fibers or bonded layers. So how do we detect reliability failure? This product reliability failure, it can be initiated by a number of different factors, complex ones at times as well. Many failures are corrosion induced, which is the failure mode we're going to be focusing on today for this presentation. So circuit assemblies are a complex mixture of materials that have seen multitude amount of processes whilst they're being built. They're then exposed to thermal and humidity cycling with condensation events and absorption of radicals. And by radicals, I mean active chemistries with ionic charges. And of course, nowadays, electronics are exposed to ever-increasing harsh environments in end uses. So some more of the challenges that we have that are occurring. So increased packaging density. We all know that things are getting much smaller, so diminishing conductor spacing. These can significantly affect the electrochemical performance and reliability of end product. Some of the challenges that we see in relation to SIR and where we see failures can occur with low voltage effects as little as 40 to 65 volts, sometimes with high current, but less than 1200 amps. We also do lots of SIR work with high voltage capabilities with up to 400 volts to 1250 volts. We've got some customers doing up to 4000 volts actually as well. And sometimes you also see things at low current with less than 50 amps. So it's a very broad spectrum of challenges and issues that can be faced when looking at SIR. Moving into sort of the space and medical world, we are working and have seen many examples of issues that occur with less than 2 volts, with less than 50 micron track spacing and roughly a picoamp of current. So it's quite interesting that even that we can see some SIR issues. So courtesy of our friends at Robert Bosch, thank you to them for this diagram. This is just a description of modern electronic control units and the products inside the products. So in this case, of course, in the car, there are a number of different products that are made. And with these requirements, you've got things such as miniaturization, you've got high voltage and current applications, you've got increased lifetime, expected and increased lifetime. And then you have to factor in the product design. So what's the material, what's the housing concept, what's the chemical interactions going to be in that design, and then knowledge of detailed cause-effect relations as well. So there's lots of issues and things to consider when we're looking at this sort of testing. So I'm going to hand over to Chris now, and he's going to talk a little bit more about the drivers for electrochemical migration, which is the effect that we're looking for. So Chris, if you're there, you could take it on. Just check you're not on mute.
Hello. Thank you, Andy. So we're going to talk about electrochemical migration. Interested in the circumstances under which that can occur. As you can see from the Venn diagram on the right, there's 3 factors that are key to this. One is the electrical bias that can drive the chemical reactions, humidity, because we need a conductive layer, which in this case obviously would be water, and then we need to increase the ionic conductivity, and that is probably coming from contamination or adventitious things that have fallen onto the board. So the humidity is important because that provides the media through which ions can migrate, and the ionic contamination produces an excess of ions above that from pure water, which can help to lead to corrosion. Next slide. So here's a schematic, perhaps, of what could be a BGA. So we have a an anode and a cathode, and we have filled up the space between the component and the board with a moisture layer, which is now quite thick, obviously, with the size of the solder balls. But in SIR on open combs or other parts of circuit boards, we'll have a very much thinner water layer, perhaps less than 100 nanometers. And hence these pathways can become quite tortuous and not, as you can see here, which you have presumably a relatively easy flow for the ions. And so on the anode, we get the corrosion. We produce cations, which will go to the cathode, and at the cathode, they will give up their charge, and we see a dendrite growing out from the cathode. We also mentioned sort of other electrochemical flow, like electrophoresis, electroosmosis, as well as electromigration. All these current flow mechanisms are relevant to the process, but it's electromigration that is the important one and leads to corrosion and generation of cations which flow in the gap. The next slide, please. So we can see some of the chemical reactions that are going on here. So the anode is now on the right. We get metal ions dissolving into or coming into the electrolyte and being pulled across to the cathode. Depositing at the cathode, they become metal again, and that's how the formation of the dendrite occurs. But we can also have the opposite occurring when there's a very limited amount of moisture around and solubility is an issue. So in terms of anodic migration phenomenon or conductive anodic filamentation, subboard phenomena where moisture is limited, we get conductive salts being formed. So they by contrast grow from the anode towards the cathode, and they are very much dependent on the moisture being left in the board for conductivity. So they can form a short during their use in the field, but when they get back to a lab or to have some diagnostics run, that resistance may well have disappeared. And all of these electrochemical migrations are often attributable to no fault found when a product is returned from the field. Next slide, please. So here's some examples of dendrites. On the left, we have a capacitor which shows a dendrite that's grown across the top. So they're not always across the board surface. The components themselves can suffer this type of failure. The next picture shows an SIR pattern, where at the top we have the anode, which is corroding and changed color, and the migration to the cathode. We've started the metal precipitation process and growth process, and you can see a dendrite growing back towards the anode. In the third picture, we have a conformally coated board with gold wing leads, and we're growing dendrites across the top of the coating. So they don't always have to be on the board surface, they're just on the top surface where moisture can be absorbing. And here we've got clearly sharp edge coverage issues as the current flows from one anode to the cathode from the sharp edge. And the last picture is just another example of what corrosion products could look like in electrochemical migration. The next slide. So again, an image from Robert Bosch. So here we can see failures developing in this zone at the bottom of the picture, and this is after 500 hours. So these failures don't always happen instantaneously. Typically, they need at least a week, but they can be weeks and weeks. And so 500 hours is typically about a month's worth of testing at the 85 85 conditions. So you sometimes have to wait some while before you'll see this failure mechanism. We're well aware of high voltage as being very much an issue today. We're seeing a lot of failures in different parts of the assembly. They could be obviously subsurface in the board, CAF or AMP. They can be on the surface, but they can also be in the solder mask, or they could be in the coating as well. And the second image shows you a typical high voltage failure. The top right picture shows a dendrite which is grown under a condensing condition. And here we obviously can see the dendrite, but in condensation testing or dewing testing, it will find a failure very quickly. But if it doesn't find a failure, it will never fail. So it's a much faster test. The failure in the bottom left, you can see it's gone from the Goldwing component up towards the capacitor. So you can get long distance or scale of material diffusion that leads to failure. It doesn't have to be always a very short pathway. It can be sometimes develop over long pathways. Again, in the middle we see a capacitor where we've grown a tin dendrite across the top of the capacitor. And finally, the last one, again in a condensing environment, we can see the effect of what's happening with the leaching out of entrapped residues that are spilling out and being pulled out, and then resulting in a corrosion over a wider range of, over macroscopically a wider range than just a fine dendrite. The next right. Yeah, so here, just summarizing this, so with typically where electrochemical migration is concerned, we need bias. So bias and environmental conditions always prevail. So when we're concerned, or it is an issue, it's on an electronic circuit board. It's in a harsh environment, and hence the board must be able to withstand or work in these environments. If it doesn't, that's going to likely to be due to ionic residues. And this is more an issue that relates to how the board was manufactured. So there are many possible sources of these ionic residues. Typically, most concerning, or the one we must pay most attention, is the flux residues, because there are deliberately acids inside the fluxes which need to be controlled or removed or neutralized during manufacturing. Then there are other issues such as improperly cured coatings or poor board materials or just generally contamination. So there's a number of issues that must be controlled under a good manufacturing process to avoid this release of ionic ions. Next slide. So this is just talking about sort of more about the issue of entrapment. So under the components, the flux residues could remain, or some ionic contamination, and they could be quite well bound in. It could be difficult to remove, or it can be difficult to test to see if they're there. But SIR testing will tell you whether that residue is harmful. By applying a bias on an SIR pattern underneath this component, we can see if there is any mobility, is there any charge flow, will there be any corrosion. So SIR is very useful in investigating this entrapped, potentially insoluble residue, which may create a problem in the future. Next slide. So what is an SIR test? It's measuring a leakage current, which we're converting into a resistance. But what we're measuring on the circuit board is a pattern which has an interdigitated comb or overlapping fingers, as a very small sort of schematic is shown there. And this overlap between anode and cathode which keeps heating gives you a better opportunity of capturing an event, and it also gives you a geometric amplification for actually measuring the current. The test itself, as we've seen, is dependent on the test voltage, the test pattern, and the environment, the temperature and the humidity. Obviously, as the temperature and humidity increase, so does the thickness of the water layer. Next slide. So one of the really important things about SIR testing compared to anything else is that it's measuring an electrical parameter. It's measuring the leakage current. So it has real meaning in terms of what a future product is going to, how it's going to perform in the field. It's not just telling you that there's a certain chemistry on the board, which may be important, but it may not. And the SIR pattern is geographically located in particular positions, and it can be part of a component termination set, or it can be underneath a component. So we also know where the SIR issue is because we're measuring a pattern which is related to a component. So the SIR works by driving in a current in this damp heat environment, and it's essential to form this adsorbed water film, which acts as our conductive layer. The electrical bias used in SIR testing drives these ions from either backwards to the electrodes, and contamination residues supply an excess of aggressive ions, which help that current to flow between the two electrodes, causing corrosion. The whole process is we call an electrochemical migration, and hence SIR measures that susceptibility of electronics to electrochemical migration. Next slide. So this is just a little table which sort of gives you an idea of where these different techniques are used. So across the top, we have the different techniques, which is SIR, Surface Insulation Resistance Measurement. Next one is solvent extraction conductivity measurements following the process ionic contamination test, PIC. Then ion chromatography, then Fourier transform infrared, then a short SIR test, and then a full assembly test. And we're looking at sort of how long does it take to fail? Was the test destructive? Am I actually testing the product? Can I generate a go, no-go test? And then I got some process characterization, process verification, and process qualification. So only the full assembly test will give you the answer to all of those issues, but you have to have a product to do that. Short SIR is really not very applicable. It's only potentially useful as a go, no-go type test. On the far left, we can see that the advantage of SIR is it can give you a process characterization, it can give you process verification, and really it's the only test that gives you a proper qualification because it's the only way to measure the material set. And it's very well complemented by PICT, which you can see we have the green boxes on the bottom of the table, and on PICT we have the green boxes on the top. So we have for PICT, it's non-destructive, it can test the product, and it can produce a go, no-go type answer. And a chemical test like ion chromatography and FTIR, they're more useful for investigations when you've found you have a failure and you want to find the source. So that just helps to put in context how these different techniques work together. Next slide.
Okay, well, thank you, Chris. Yeah, so I'll take it on from here. So Some of the capabilities and constraints of SIR testing. So SIR test coupons and board designs should always represent the real production reliability. Standard test coupons normally use typical components that might not fully match customer needs, but SIR patterns can be customized to include representative components for application. Using SIR with supplier provided coupons results in process qualification. So SIR is the only test that qualifies the material set. So whilst full assemblies can't be tested, dedicated SIR vehicles or generic representative boards can be used to reproduce operating conditions for qualification. And then legacy requirements, so single time point readings. These suffice for modern complexity. So all of the legacy things don't fall in line with today's technology. Obviously, as we already discussed, with modern components already having smaller gaps and higher voltages, these failures could be then possible within minutes. So with that, continuous or frequent measurements are now needed in the measuring device, and some of our equipment, for example, can monitor up to 256 channels per minute. So just addressing some SIR misconceptions. The first one is to say that on the left, we've got a misconception. So SIR test coupons and board designs always represent real production reliability. So not quite. So the board and coupon geometry, as well as real assembly contamination, critically affect the outcomes. Not all SIR data is transferable or meaningful unless test vehicles mirror real products. Another misconception is passing SIR with supplier provided coupons equals process qualification. No, a correction to that would be using a SIR test vehicle that's representative in terms of component geometry, entrapment sites, and residues is the only way to demonstrate process qualification for susceptibility to ECM. And then another misconception, so legacy requirements, which can suffice for modern complexity. No, as already highlighted, frequent monitoring with multi-channel SIR is the only way to capture fast transient effects seen with dendritic growth or ECM effects. So understanding some of the dependencies in SIR testing, reproducibility issues. Why can SIR results vary sometimes? Mainly, we find that a lot of the issues can come due to sample preparation and handling. Also, issues with entrapped residues under components, which are highly variable and can cause failures that can only appear sometimes temporarily. Some of these potential reasons can include sample preparation inconsistencies, entrapped residues, handling issues, even environmental conditions. You could even add cables that are being used. You know, if cables have been in use and have been in the chamber, being subjected to these environmental impacts for, say, up to a year of testing, those cables could fail as well at some point because they're exposed to this same harsh environment. So really, variations can occur due to these preparation inconsistencies, but maybe improper handling. These can create false failures. Then when we're looking at production and process control issues, what are we testing? So understanding the time sensitivity of ECM failure mechanism. So a manufacturer's SIR data might not reflect actual production unless test conditions are closely matched. So this is one of the reasons why SIR is not really suited for process control, as tests take around a week and cannot be performed on full products. Some of the issues are the edge sections. So when you have snap-off sections of a board with SIR circuits can provide some data, but they're not fully representative as they don't experience the same reflow profile. So they're not experiencing exactly the same thermal, what's the word I'm looking for? Thermal effects as they would in the center of a board as you would be at the edge of a board. They're also expensive to do. So for process control, that's where the solvent extract conductivity or ionic contamination or the SEC or ROSE methods are more appropriate. So what does a failure look like? So we'll talk about this a little bit later, but SIR requires resistance to stay above 100 megaohms. So whilst 100 megaohms can affect analog circuits, digital circuits are generally more tolerant and catastrophic failures can happen when metallic shorts form, dropping resistance below 10 kilo ohms. And on the right, we've got this graph here just showcasing the blue line kind of being a normal test, you know, no real issues. And then we've got examples of failures that have occurred with the pink and red lines, even the green line, and resistance has dropped, so you know there's an issue there. That's just what a kind of example failure would look like with SIR. So what's been the direction of travel for SIR testing? Some of the conditions. So environmental tests remain mostly unchanged. So generally it's always been 85 degrees centigrade and 85% relative humidity for rosin flux. And then for modern weak acid fluxes, generally it's tested at 40 degrees C and 90% relative humidity. And then for conformal coatings, generally it's at 85 again. Test frequency and voltages have changed significantly. Early bell core tests, which are back from, I think, 35 to 40 years ago, measured 3 times over 7 days, sometimes with bias reversal, so using plus 50 volts for conditioning and minus 100 volts for testing. But with the latest equipment that's available today, the frequency of measurement on a single pattern can be less than 20 seconds and can measure 256 channels in 1 minute. So hence rapid growth of dendrites can be followed in detail. With today, some of the SIR fluxes are tested at less than 5 volts, and some solder masks are tested at more than 1,000 volts. So modern equipment has been updated with temperature and humidity standards, making results more predictive for today's assemblies. So this next one is just a quick example of a SIR measurement, a temperature and humidity controlled chamber you require. You need the measuring unit itself as well. Of course, then you need the coupon itself. And on the right is just an example of a test rack with coupons that are situated inside the environmental chamber. All of these areas, test board design and test condition, are critical to the test. So Chris is now going to talk a little bit more about the test pattern. Chris, if I can hand over to you again.
Thank you, Andy. So our SIR patterns are two-dimensional, and we think of when we measured resistance across our two-dimensional space, we like to think about things in terms of squares. The resistance of a square, irrespective of its size, is always the same, because in our 2D world, if the square is getting bigger, then the width is also getting bigger, and the height is getting bigger at the same ratio. So the resistance remains the same. So when we look at our SIR pattern, we like to think about how many squares can I make up sitting between each electrodes in all of those interdigitated cone parts, so we can count those up. So it turns out that the resistance of the pattern is simply the resistance of the square divided by the number of squares. So we get a geometric amplification, and hence we can measure resistance. We can measure lower resistance than actually the resistance of that square, and that helps us with the equipment, because otherwise we'd be measuring much higher resistances. Thank you. It was a big study I led quite a while ago, where we looked at the design of these SIR patterns, and we took into account a number of different variables. So one was the field strength across the pattern, and you've got values there from 10 to 400 volts per millimeter. We looked at different gapped patterns as well, and we had gaps from 100 up to 500 microns. So the 400, 500 is the B24, and the 350 is close to the B25. The patterns all had the same geometric size, and you can see that the number of squares changes considerably. So we go from 31,750 squares at 100, down to only 1350 with the B24 pattern. And there's some other test conditions there that was principal test conditions for the experiment. We've seen one of these results before, so but the important thing about these two graphs is they were both done with the same field strength of 200 volts per millimeter. But one was done on a fine pitch pattern at 200-200, and the other was done on the 400-500 with a much wider gap. And you can see that on the left SIR result, we didn't get any sort of corrosion events happening, whereas on the right graph we did. So those failures electrically are showing us effectively when a dendrite grew, and there's some images on this board showing all the different types of dendrites that we observed. So test pattern is a critical part of our choice. And on this slide, we just show you that there's no one size for SIR patterns. They come in all shapes and all sizes. So the B52, which is for a process validation experiment, that B52 being an IPC code, we get all the different SIR patterns that fit to those particular coatings, components, sorry. Whereas the one on the pattern on the left is for the newest pattern that's available, B53, which is for flux and coating qualification, and that has a 200 micron gap pattern, the B24 500 micron gap pattern, and the B25 318 micron gap pattern. So there are standards. The first one, IEC 61189-5-501, that's an IEC standard for SIR qualification of fluxes and coatings. It's a plain board. It's very similar to the IPC 2637, which is also for the same purpose. The next one, the 61189-502 document, that's for components on a board. That's the only test method around at the moment that actually gives you a full test method for testing that type of board. In IPC, though, we have a couple of very useful documents, which are guidance documents, and they tell you how to go about an SIR test and how to test or run an experiment to do the B52 test board.
Okay, thanks, Chris. So yeah, so going on from that, so this is we'll talk about a little bit of using the B52. This is just an example. This is the same for any test coupon, but if we just, for the sake of this slide, wanting to use the B52 to do some testing, what's involved? So you follow the IPC 9202. You'd need a test coupon or multiple of. You'd need a test chamber capable of providing the well-controlled heat and humidity. You'd need a precision measuring system. You'd need the interconnecting cables. And finally, you need to have a way to collect the data and have graphical interpretation. So those are all the things that would be required when running an SIR test. It's not as hard as you might think, and easier certainly than it used to be. So when you want to consider these aspects, you want to select your process suppliers, what board, what finishes you're going to have. You need to purchase the kits of dummy components, then process the coupons as per the end product, then place it into the test rack, which is highlighted here. This is an example of a test rack that we make, and put that into the environmental test chamber, get it up to temperature, and then sit back and relax for a week whilst the test runs. So that's a very simple way of what you need to do when running SIR. Moving forward, there's new advancements in technology and ways of doing SIR, and we're going to talk about a brand new technique that's been developed recently, and hopefully this video will play whilst I'm showcasing. But this is a new technique that we've been working on, which is condensation testing. And condensation is the ability to simulate and control localized condensation on electronic test boards during damp heat testing. So it works by adjusting the temperature of the test board independently of the test chamber's environment, and can adjust the test board temperature precisely to 0.01 degree control to at least 2 degrees below the dew point. So why is this useful when talking about SIR? This gives the ability to see real-time monitoring of how moisture and condensation affects different board designs, spacings, coatings, giving an insight into water-based failures. So when I'm talking in this context, when I mention moisture, what I'm referring to is traditional SIR damp heat testing. Oh, sorry, gone too far. So water layers that are less than 100 nanometers thick, whilst condensation refers to the macro water layers, i.e. like microns to millimeter thick. So this new technique has been utilized because traditional SIR damp heat testing can miss critical coating defects. So by creating this controlled water film on the board surface, it can trigger early stage failures such as dendritic growth and insulation breakdown, most importantly in hours, not weeks. Going forwards with condensation, this graph in the top left is showcasing the control. So each step, each green line here that you see here is a step going down of temperature at 0.1 of a degree. And what we're looking at is a dew point that is at 37 degrees. And we're measuring on these sort of red and blue lines what the resistance is here. And when we get to 37 degrees, there's a very, very thin layer, and we can start to see some resistance breakdowns. 0.1 of a degree later, bang, we see resistance drop. So this is showcasing the effects of the condensation on the board and the impacts that it can have. And the fact that we can now see this at 0.1 of a degree differences showcases the effects that can occur. So this is critical to understand the effects of condensation and can highlight potential failures that may occur. And a very important statement is condensation will cause failures that cannot be seen in normal damp heat testing. It will also happen in hours. So just to summarize quickly, so the SIR technique is the only test to produce data that directly relates to circuit performance. In SIR testing, we want to see the highest resistant values. SIR results can be used to qualify material set and manufacturing process. SIR test is given in standards, but the key parameters are temperature, humidity, a bias voltage, and the length of test. And new techniques are constantly being developed, such as the condensation technique, taking SIR testing to the next generation. The next one we want to talk about is ECM, electrochemical migration characterization approach. So whilst SIR measures the residue effects directly linking to circuit performance, it's the only technique for this, but it's slow and requires a special test board and coupon. So we're going to talk about the SEC, so solvent extraction conductivity or ionic contamination method, which checks manufacturing quality. So SIR qualifies the process, and similar boards are then tested with SEC to generate a reference. So production boards are generally periodically checked against control levels set by this method. This was, of course, known in the industry as the Rose test with a single control limit, but it's since been corrected in IPC J Standard 1, Rev H, with the removal of the Rose 1.56 micrograms of sodium chloride. So Chris will quickly go through the principles of this.
Thank you, Andy. So solvent extraction conductivity testing, we have an alcohol water solution into which we put our product, our surface test assembly, and we dissolve off the ions, which then pass through a conductivity cell. So we measure the residue that can be dissolved off. And this approach has been around for more than 40 years. And we have, as Andy just mentioned, it was previously has been known as the Rose technique. And it had a pass-fail level. And that pass-fail level came about from the technology at the time the test was brought into existence. And at that time, back there, if we think about the number of joints per square centimeter we might have seen, it might have been around two joints per square centimeter. And if you look at the pitches today, which is quite common to see 0.4 of a millimeter pitch with 150 micron gap. So they could be down. So that would lead to more like 200 joints per square centimeter. So there's been 100 increase, 100 times factor increase in the number of joints, and hence you get the opportunity for residues to be dissolving off has gone up 100 times, but the 1.56 hasn't changed. And so this is something that the new PICT method and approach looks at in terms of trying to establish what that metric should be. And that metric comes from the SIR process qualification. And then we can take that knowledge to then build up a library value for particular boards, which gives us a pass-fail. So now we have a tool that works in a short period of time and gives us a go, no-go value or control limits which we've established by an SIR investigation. The advantage of the technique is that it's fast, it's repeatable, 15 minutes, and its repeatability has been proven in a study by Robert Bosch, where they achieved 6 Sigma verification in terms of their processes using this sort of very instrument, this approach, and a machine provided by GEN3. The disadvantage of the technique is that it won't remove all the residues, but it won't remove all the residues every time. It's a process tool. It doesn't matter if it doesn't remove them all. It just matters if it does the same thing every time. So it can flag a process whether it's getting better or not. There are some differences in the available equipment around, and you have a closed loop or a static tester, and you have an open loop or a dynamic tester. The big difference between these machines is the amount of volume in the ancillary pipe work that's going on. In the closed loop system, it shuts out of the ion exchange column, which is used to clean the liquid before the test. In the dynamic or open loop tester, the ion exchange column is always in the loop. So the volume in the system is greater. And this volume is important because you divide the contamination by the volume in the system to get you your loads. If you've got a bigger volume, you've got smaller sensitivity. And the big thing also is that if you have a closed loop system, the contamination slowly builds up. So it's very easy to measure your endpoint with the test. With an open loop system, you're integrating an electronic signal. And as we get close to the end of the test, we're into noise issues. And it's very hard then to get to a precise endpoint and know when to stop the test. So the test could go on for a longer time. It could continue to pull out extra ions from the substrate, which you don't really want to see. Next slide.
Okay, yeah, that's back to me. So thank you, Chris. So ionic contamination, or contaminometers as ours are called, are ideal for checking from components to production boards that contamination levels are within limits of reference values. So this approach is described in IEC 61189-5-504, which is the general test method for materials and assemblies, otherwise or known as process ionic contamination testing. This method supersedes the historical Rose approach of having a fixed pass-fail criteria of 1.56 micrograms of sodium chloride. This value was used irrespective of the assembly technology. So the ionic contamination is the only process control tool for tracking the ECM effects of harmful residues in a timely way. So what happens if I have a failure? What next? So if SIR or PICT data reveals a failure, a root cause analysis investigation is undertaken. So these causes can be with current material selection, could be with a batch problem with fluxes, could be a reflow oven problem, and multiple potential causes. And this is where chemical analysis of the residues can be undertaken using things like ion chromatography, which help identify the specific ions which can be tracked by fingerprinting to library values. Other techniques can be like FTIR, Fourier transit infrared. And these latter two can be undertaken by labs specializing in these techniques because they are expensive, they're difficult to do, they're complicated to work out, and so really should be only used for root cause analysis. So expertise and equipment are expensive and infrequently used. So establishing the reliable manufacturing process. So the summary of what we talked about today. So we've talked about the underlying causes of ECM failure, which have been discussed. We've talked about how SIR works and how it can produce direct and meaningful data, evaluating the material set in assembly, and its processing has also been shown. We've talked about the procedure for conducting SIR measurements. We've also talked about process control and catching anomalies using the PICT approach. We've also talked about new technologies for SIR style testing, which was the focus on condensation testing as a new way of seeing of doing this type of SIR style testing. And then finally, we talked about root cause analysis with ion chromatography and FTIR, which described how they can be used for analysis when failures occur. And with that, we'd just like to say thank you very much for listening in. Hopefully we're not stretched too far on time, but thank you very much. And we welcome any questions that may have arisen during the course of this presentation.
Thank you, gentlemen, for the presentation. We do have a few questions that came in, but just as a reminder, feel free to use the questions panel at the top right, indicated by the question mark, to submit any of your questions. Questions that don't get addressed today can be addressed separately, because we do just have a few minutes. One of our questions, gentlemen, is around reliability. So how reliable is the short SIR test, which is conducted for only 2 hours? So under what scenarios would it be more reasonable to use this method?
The SIR test is measuring electrochemical migration, and you have corrosion at the anode, and then you have transport of the ions across the gap to the cathode. Characterization done across many papers, many literature by many workers, shows that these effects don't generally occur in anything like 2 hours, and we can sometimes be having to do measurements up to 500 or 1,000 hours. So SIR doesn't really lend itself to a fast test. It's looking at a different phenomena.
Thanks, Chris. Another one of our attendees asks around how do I decide on the right test coupon and accompanying SIR test pattern?
So here, this is, I think, a question that refers to what's in the IPC 9202 and 9203. There we have a suggestion, a design with 16 components on there. And you can use those 16 component types as your standard go-to measurement. They were chosen as weak links or things that should be of concern across the component range. But that is not, it was never intended that that should be always those components. And so a user of that standard is always at liberty to redesign the board to have a different set of components and do something different. When that board was designed back in about 2003, that seemed like a very good stake in the ground. But perhaps 20 years later, that design's getting a little tired. So I think it's horses for courses. You can still use it as it is, but it is quite easy to sort of see why people might change and use something a bit different.
Okay, thanks. Could you discuss a bit more on concerns using PICT-SEC for evaluating residues from no clean fluxes versus post-clean aqueous wash processes? We've had suppliers express concerns with running no clean assemblies for fear of contaminating the system.
So could you just read the first part of the question again, please?
Sure. Could you discuss a bit more on any concerns using the PICT-SEC for evaluating residues?
Okay, I mean, no clean fluxes shouldn't be, they're designed not to be cleaned, but the cleaning chemistry industries have found ways to clean them. When we clean them, what we're worried about is sort of ionic material that might be free and is mobilized into the solution. SEC is a good general technique because it is agnostic. It's not looking for any particular chemistry or molecule or ion. It will just, if it's charged ion, it will be measured. So it's good at doing that. If you see peaks or higher levels in an SEC measurement, in a contaminometer measurement, then that your curiosity is piqued and you would like to know what was causing that. So then you might think about going to ion chromatography to find that out. I think, hopefully I've answered that question.
Okay, this is a little bit around interpreting results. So when your SIR test shows a resistance drop, say well below 8 megaohms, but recovers above 8 megaohms for the remainder of the test, what does it tell you?
Well, in the first instance, you've had a failure, and that initial point of failure may be enough for the equipment to be considered to be US, and hence you take it out of the field and you send it back. The fact that the short or the low resistance pathway was developed and was there stable for a period of time, but then collapsed, is just that whatever the chemistry involved with that short circuit, it's not particularly stable, and that over time it then broke down again and the resistance recovered. But the important point for me as a manufacturer is I saw a short circuit occur at 50 hours and then it disappeared again at 100 hours. It's not happy days really, because I don't want to see that short at all if it developed at 50 hours.
Okay, we'll sneak in one last question. Can you help a manufacturing engineer outline a product and process control methodology for production? How can a process engineer engage with GEN3 and Zestron to develop a material set, verify processes, and have those control methods in place for their production?
So that is quite clear, I think, hopefully. You build a board like a B52, which so you have the right designs or components on that board. You use a board fabricator to build this board that you use for your current products. You manufacture it in exactly the same way that you do today with your current process, and you clean it in exactly the same way. You then go away and you do your SIR test. If you've passed that SIR test, that's good news. If you haven't, you might want to revisit the process or the cleaning process to improve that. When you get to a point where you're happy with that process qualification, you've effectively said, my material set is good. I like this process I have, and the materials are all behaving themselves. I now make a product board with that material set, and then I immediately do an SEC test, a contaminometer test, and that hopefully reflects exactly the material process you use to do the SIR boards, and that becomes your library value or your golden value for that particular board in production. And then you refer to that as and you can set some reasonable control limits around that value. That's where you go from there. And then periodically you measure with the contaminometer every week or every day, every week, every month, building up confidence on your process. And if it falls outside the control limits, it's a red flag that something in the process has now gone wrong.
Great, thanks, Chris and Annie, for your presentation. And on behalf of Zestron, I'd like to thank all of our attendees for joining. We certainly appreciate you spending your time with us, and we'll be posting future webinars on our website and our social media channels. So we hope to see you again shortly in the future. But thanks again to our guest presenters from Gen3 Systems, Andy Naisbitt and Chris Hunt. And
Thank you.
thanks so much.
Thank you very much.
Thank you.